prove that solenoid acts as a bar magnet. What is the difference between this and this? Here I said bar magnet, here I said magnetic dipole. Is there any difference? Both are same. Okay. So different places they will use different words. So don't get confused by the names. So magnetic dipole is nothing but bar magnet. Magnetic dipole moment is different. So when you say moment, you have to write the formula. It's a value. Okay. So we are talking about solenoid like this, right? But then in this particular case, I am going to show something like this to make it easy for us to represent this. So let's say if the current is going like this, so the coils are coming out like this and then going in here. So that means here it is going, what is this? Into the paper. Here it is out of the paper. Okay. So when a coil comes out like this, it goes here, comes here, just keeps on going. So instead of showing it like this, we can show it like this. I'm going to take the center point and then we are going to do a little bit of so suppose if I take a small distance dx at a distance of x from the center, right? And I want to find the magnetic field at this point, which is R. So I want to find the magnetic field at this point P. So using the same formula, right, I am going to write it as dB is equal to mu naught by 4 pi 2 pi a squared. So this is my a, this is the radius a, 2 pi a squared divided by a squared plus x squared power 3 by 2. But this is for one single coil, right? But suppose in this case, what am I having? I am having a lot of turns, right? So when you have 100 turns, what should I do? I should multiply by 100, which means I should multiply by the number of turns. So I should multiply by number of turns. But the number of turns, so initially I am going to consider only this small thing. So I hope you have been introduced to integration in your mathematics, okay? So this part alone, if I want the number of turns, I am going to say it is, so n is equal to number of turns per unit length. Just to make it easy for you, let me say I am going to say n is equal to 10. That means you have 10 turns per meter. Okay, if I say 10 turns per meter, so for 2 meters, how many turns will that be? 20. For half meter, 5, right? So what did you do? You simply multiplied n into that length, right, to get the number of turns. So if I want number of turns here, what should I do? N into this distance. So n into dx. Okay, which means that will give me the number of turns in this particular thing. Why did I put dB here instead of b? Why am I putting it as dB? Only for a small thing. So for this small, from this small region, how much will be the magnetic field at this point? So the small magnetic field due to this small dx. Okay, that's the meaning of this. So I know you, all of you are kind of new for integration stuff. So let me write it as small magnetic field due to a small length dx. Okay, that's why we are writing it like this. So that means I am going to write this as n dot dx here, number of turns. So After this, it's very simple. So I'm going to do the same assumption here. A is very, very small compared to R. Okay. So which means I'll be saying that A is very small compared to R. And then X will be taken as, okay, in this case I took it as same, but here I am integrating it. So that means I should not do that one. Okay, I've done a small mistake here. So I'm considering only this dx, right? So that means if this is from the center, this distance is r. Okay. So what will be the distance of this coil from here to here? R minus x, right? So this is very, very small. So I can assume that if this is r and this is x, this distance is actually r minus x. You agree? So that means the a squared is radius, but this x is this one. So x squared should be replaced as r minus x the whole square. Everyone okay with that? Because we are considering this small element. So that means what is the magnetic field at this point due to this small element? Which means I should consider only this. Okay. So the issue here is earlier in the circular loop, right? There was an axial point. So there was only one x. But in the solenoid, what happens? From here, the distance is different. From here, the distance is different. So at every point, the distance is different. You understand what I am saying? So maybe this will be contributing more magnetic field. This element will be contributing less. This will be contributing even more less. And this will be very, very low. You understand what I am saying? Because of the distance. So that is the point where, that is why we are using integration. Because at every point, the magnetic field is going to be different. Are you following it or not? Anybody having any issues? No? No? Okay. So let me repeat one more time. This is closer to this point and this is farther. Which one is going to provide more magnetic field? This one or this one? This one, right? So that means at every point it is going to provide different amount of magnetic field. It's not going to be the same. That means I have to take a general point and then I have to integrate from here to here. By that way I will be getting the total magnetic field. That's all. Since the things are changing at every point, I cannot simply use a direct formula. I have to do some integration. Is that clear? So coming back to this, mu naught by 4 pi I 2 pi a squared divided by a squared plus r minus x the whole squared power 3 by 2 n into dx. And then just like what we did here, I am going to say a is very, very small compared to r and x is also very, very small. So let's say this is a solenoid very small, whereas this distance is very high. Okay, these are some quick assumptions to make it easy. Okay? Otherwise it will be a very difficult integration. So if I want b, what should I do? I have to integrate it. So that means mu naught by 4 pi is a constant, so it doesn't bother me. Current is constant everywhere, right? What is the current flowing here? I. What is the current flowing here? I. Everywhere it is the same I, which means it is a constant. 2 pi a squared becomes area A, right? So pi a squared can be written as area A. Then this a squared goes away because it's very, very small. X also goes away, so what I will get is I will get r cube. The only extra thing which I will be getting here in addition to this one is all the others are exactly the same, only the n dx. Number of turns is also constant, right? Number of turns per unit length is constant. n. It means dx. So here all these things are constant, which means I am going to put the integral symbol only for this one. But where am I integrating this? I am going to assume that this is distance, this length of this solenoid is taken as L here, and then this is L here. So that means this side I am going to say minus L to plus L. Do you agree? Because this is my center point, so I have to integrate from here to here, all this here. Everyone okay with that? So integration is going to be a little bit difficult, but still you will have to learn these techniques, okay? Once you start doing these derivations, it will get better. Particularly for your entrance exams, you'll get a lot of questions based on this integration methods. So I'm going to say I'm integrating from minus L to plus L. Maybe you are not being introduced to definite integrals yet, but you know upper limit minus lower limit methods. So mu naught by 4 pi. What is NIA? NIA? Yeah, but then that is number of turns, right? So it's not just small n. Okay. So I'll leave this 2ia n by r cube. So integrating this will give me integral of dx is x integrated from minus L to plus L. So it will be upper limit minus lower limit. So L minus minus L. So it will become L plus L, which is 2L. Do you agree? So that means mu naught by 4 pi. So I am going to erase this one. 1 by 4 pi. 2ia 2 divided by r cube. This is 2 or n? It's n. So this becomes L minus minus L. So which means I'll directly write it as 2L. What can you say about, which one? Yeah, we'll come to that. But as I said, generally I like to keep the mu naught by 4 pi separately, okay, because it's a constant. Anybody remember the value? Mu naught by 10 power minus 7, okay. So if you keep those constants separately for your numericals, it's easy, okay? You can keep it separate. So what is this? N into 2L? Capital N. Why? Because 2L is this total length. Small n is number of turns per unit length. Okay. So small n is number of turns per unit length. That means n into 2L will give me the total number of turns. Anybody having doubt in that? Because the total length is 2L. This is L, this is L. So the total length is 2L. So 2L into small n will give me the capital N, which is the number of turns. That means I am going to write it as mu naught by 4 pi 2ia n divided by r cube. What is NIA? Magnetic dipole moment, m. So that means I can say mu naught by 4 pi 2m divided by r cube. So what did we arrive? So we arrived at the same thing like this one. So that means you can say that it looks like a magnetic dipole due to a bar magnet, right? Everyone understood this when I talked about this one? So if I go back to your basics, you will have minus q here, plus q here, and if you find the electric field at this point, you would have found this formula. That is for an electric dipole. For a magnetic dipole, so what do you mean by magnetic dipole? South here, north here, and if I find a magnetic field at this point B, according to this formula, it will be mu naught by 4 pi. So similar to this, I can say mu naught by 4 pi 2m by r cube. But this is for a bar magnet, so take it down. So this is for electric dipole, this is for bar magnet. But what did we prove this for? We proved it for a current carrying loop, which means this will also act as a magnet, bar magnet. That's what we are trying to prove here. Okay. Same thing here. So if I had a solenoid, I am getting the same value here. So write down the same thing. So comparing this comparing this with magnetic field due to a magnetic dipole or bar magnet. We can say solenoid acts as a bar magnet. So solenoid acts as a bar magnet. So that's your second derivation. Okay. Electric dipole inside a external electric field, which looks something like this. We have studied this earlier. So this is my electric field. If I put a minus q, then a plus q here. So we said this is theta. And what will be the torque experienced by this? P cross E. I told you it's tau P, right? Easy way to remember is tau P. Okay. So we can say tau P and you'll get this. Okay, this is nothing but P sin theta. So this is my dipole moment, this is my electric field E, the external electric field, this one. Okay. So anybody remember how we arrived at this? Using this, sorry, not this one. So using this, we arrived at the potential energy here. So if you remember, we did something like U is equal to work done is equal to force into displacement. Whereas rotational work, so since potential energy I am going to call it as U. So in place of force, I will put torque. In place of displacement, I will put theta, right? But since it is a small distance, I am going to call it as d theta. Okay. So using this, you would have substituted this and you would have found, or let's quickly do that so that it will be a quick. So it will be integral of this. So tau is equal to P sin theta dot d theta. Everyone okay with this? What I am doing here? So this is from your previous chapters where if you keep an electric dipole inside an external electric field, this is what it will show some kind of a torque. Okay. And if I am pulling it, so in this, suppose if I am taking it up to certain height, right? What is the energy possessed by this? Potential energy, right? Because the moment I leave it, it's going to manifest as kinetic energy. Same thing, if I had an electric dipole, if there is an external electric field here, if I did like this, if I pull this up like this, right? If I leave it, it will come back and fall this way. Why? Why would it fall like that? Because this side it is plus, this side it is minus. That's the meaning of electric field, right? Magnetic field is north to south. Electric field is plus to minus. Okay. So that means this plus will try to go this way, minus will go this way, which means if I pull it this way, it's going to go and fall this way. Okay. So if it is this way, I call it as linear potential energy. If it is this way, we call it as rotational potential energy, because I am doing some rotational work, which means it is rotational potential energy. Okay. Everyone okay with that? So tau is equal to P, so P is sin theta. Work done is force into displacement, but we are talking about rotational work. So tau dot d theta. Tau is P sin theta d theta. So P is constant. Integral of sin theta is minus cos theta. So it will be minus cos theta. Okay. But if you had sin theta, it will be cross product. If you had cos theta, it will be dot product. So it will be P vector dot E vector. So you can write this as vector form. Okay. But this is for some theta from 0. But then what if we are moving from theta 1 to theta 2? So if we are, so all these things we have done in the previous chapter, but I am just trying to show you the similarity. If you understand this, you can do the same thing for magnetism. What is the doubt, Hariam? What's the doubt? Only if you ask me, I can explain. So if you are moving from theta 1 to theta 2, then I should not write like this. What I should write is, from here, I should say theta 1 to theta 2, P sine theta d theta. Okay. So is equal to theta 1 theta 2 minus P sine theta becomes minus cos theta. And then I have to put upper limit minus lower limit. So that means it will be minus P cos theta 1 minus cos theta 2. Okay. All these things we already done. So sorry, here it's theta 2 minus theta 1. But because of the minus, it will become P cos theta 1 minus cos theta 2. Okay. And then we have done some special cases. Okay. So the reason I am repeating all these things is it's exactly the same thing. So if you understand this, we can do the same thing over here. Instead of electric field, what do we have here? Magnetic field. Instead of electric dipole, what do we have? Magnetic dipole. So this is D, this is M. All the other things are exactly the same. Okay. If you understood one thing, you can do the same thing over there. So all these things will repeat the same.